Welcome everyone to the opening, the grand unveiling of the Percival and Cloud webinar. We really appreciate all of you being here. And I saw from the registry list, as well as from people putting things in the chat, that we are quite a diverse group here. So if you are from time zones abroad, we also really appreciate that you've joined us today. The team that we have from Quandela, who's here to support, well, both the operations of the webinar and also to support you if you have questions or comments along the way, would be Alina, who is our content and events manager. I suppose you can see her on the sidebar. There's me, the engagement manager. I'm here to engage with you, as I'm doing right now. We also have Jean, our chief product officer, who is also very much, who led a lot of the development for the software that we're going to be talking about today. And we have Maxence, who is our IT technician, without whom we would not have the Zoom thing set up. He is he is our rock who will make sure this runs smoothly in any case. So a quick overview of some of the rules of the webinar. If you don't know already, it should have been, well, publicized to you, but to let you know very clearly, the webinar is recorded. That's so that we can share this later with anyone who maybe wasn't able to attend, who is interested. So please don't share confidential information unless you really would like to. I'm just letting you know now. And also we will be sharing the slides with you after the event. So if you'd like to take notes, feel free, but don't worry about writing down links. Alina will share those throughout the event, and we'll also share the slides with you. We're all pretty familiar with Zoom by now, but points 2 and 3, if you'd like to interact with us, you can use the chat for chatting, as some of us are already doing. Please use the Q&A for your specific questions. It helps us organize so we can get back to you and we don't miss anything. And if you'd like to speak, if you'd like to have a discussion while the presentation is happening, you are also more than welcome to do that. Just raise your hand and we can unmute you, and we can engage in that kind of way. So whatever you like, those are the options. And finally, please be respectful. We all come from different quantum hardwares and different backgrounds, and this is an open forum for us to discuss and to share. What we'll be talking about today is very briefly, in large categories, the QPU, how we can understand it from a technology point of view, and then the cloud, which is built on top, the way that you can interact with our QPU. So the development that we've had so far, as well as the roadmap, where we're thinking to go, and where your input is very valuable to us, as well as Perceval, the open source programming language and software that we use to develop applications and to interact with the QPU. And finally, we have some interactive things at the end. If you'd like to take that time to ask questions, if you prefer to ask at the end, you're more than welcome. That would be a good time to do it. A bit of context and history about the cloud. We launched in November last year, as a way for people to get excited, to engage with, to develop quantum algorithms. And since then, we've had over 200 people register on the cloud. So it is a growing community and growing quite quickly. We're very happy about that. Among these 200 users, as well as Quandela, we have about 2,500 hours of operations clocked on the simulator and QPU, which accounts for about 40,000 individual jobs. And another nice point about our QPU is that it has a 90% service availability, which means if you are operating in perhaps a different time zone, this is good for you. You don't have to be up at weird hours of the day. You don't have to wait days and weeks at a time to have your jobs done. They're handled as quickly as we can, and very quickly indeed. We've already seen from the chat that we're from a bit all over, but maybe a bit more context on that as well. The community is growing, and it's growing worldwide. So we're a French company, Quandela. We are based in France. A large portion of our user base is at least based in France, if not French themselves. We also have a lot of people in the US who are interested in this technology, as well as globally across Asia, South America, Africa, and Australia. So there is good representation both here today and on the cloud in general. And we've made some noise. So you may have seen some of the articles that have been published. These are These are ones in French, but they're also published in English elsewhere. You can find us online and using Nouvelles, Le Monde, so not just technical kinds of articles, but big important journals that you can read about us, also in technical sorts of things. And then when we launched the cloud, we also launched it with a Locathon. Locathon is Linear Optical Quantum Computing Hackathon. It was oversubscribed. We had a great turnout, a lot of interested people across both academia, industry, who came to learn about Percival, who came to learn about the cloud, who came to learn about Quandela, what we do, and how they can develop algorithms and use our software and our technology. We are planning on organizing more of these to engage with the community, so have a look out for that if it's something that could be interested to you. And finally, some representation from the community themselves. People are saying nice things as individuals, not just big newspapers. So this is an example of one such instance. Brian Siegel-Wax published a nice Medium article talking about his experience and what you might expect if you engage with the QPU. Oh, I see we have some chat going on. I'll have a look before we move on. Oh, hey, Brian. Glad you could make it. So Alina has shared some of the links to the articles that you saw if you'd like to have a click. Cool. Okay, I'll continue on. So now we're going to talk a bit more about the technology itself. We have, where am I clicking? Voila. So here we have a short visual representation of what goes on inside our QPU. What you see here is a visual of our quantum dot, which is Quandela's bread and butter. It is our single photon source. I've lost my mouse. And it is pumped such that we get single photons at a rate of every few nanoseconds. These single photons are then sent to the rest of our QPU. I'll pause here just for a moment to explain because there's a lot of things happening. This is in optics, what we would call a free space representation of the photonic circuit. But of course, this is something that would be integrated onto an actual chip, much smaller than having large beam splitters and phase shifters hanging around. You can see in the bottom left, the photons come up. They're sent to these yellow delay lines. These delay lines are the demultiplexer that makes sure that the photons arrive at the photonic circuits at the chip at the same time, so that they can interfere in the way that we expect them to interfere. Oops, I did not mean to click over. Sorry about that. So what you see in the cubes are beam splitters. The cylinders themselves are the phase shifters. And this gives us the interference that allows us to implement whatever unitary you might be interested in across the QPU, the quantum processing unit. The photons are then sent to single photon detectors, SNSPGs, cooled at 4 Kelvin. And then these coincidences that we count among the detectors gives us our strings of zeros and ones, which ultimately correspond to the calculation that you're interested in. In this case, we have a graphic of some differential equation solving. Voila, voila. Oh, now I want to move on. There we go. So here's a bit of a more compact representation of what we just saw in the video. We have our single photons and multiple waveguides. Waveguide is a bit of a jargon word for what you could think of perhaps as a fiber optic. It's fiber optics which are etched onto a chip that allow us to guide the photons that allow them to interfere, like you saw in the animation just before. The photonic circuit itself consists of beam splitters and phase shifters, which allow you to implement your unitary. This is part in the middle. And then these are sent to detectors, which are at 4 Kelvin. The photonic circuit itself is not cooled to 4 Kelvin. It is at room temperature. The detectors and the single photon source themselves are cooled to low temperatures. In a bit more of a schematic view, again, maybe a bit more detailed, we have our source down here on the left, which we call Faith, is very faithful, who produces single photons according to the pump laser. This is sent to the DMX, the demultiplexer, which makes sure that all of our photons, which may have been generated at random times, are sent to the photonic chip all at once so that they can interfere in the way that we expect them to. This is where your unitary is implemented. This is all sent to SNSPDs, the time tagger that allows us to count coincidences, and this is all controlled by a classical computer down below. It's important to note that the photonic circuit itself, the photonic chip, is something that you can get, well, it's a well-understood technology. It's something that you can get from multiple vendors. In fact, we have multiple suppliers for our photonic chips. The detectors are well understood as well. Here's a transcript. The detectors are well understood technology also. These are things that you can buy off the shelf from various different suppliers. The magic of what happens chez Quandela, at Quandela, is really the single photons that we generate. We have a high source brightness. What this means, if you're familiar with optics and single photon sources, we don't use the kind of typical parametric down conversion or four-wave mixing source. We have a source which is, in principle, can be unitary efficiency, which is kind of a push button source that you would imagine. We're operating about 50% brightness right now, but this is something that we improve on all the time, that we're continuing to work on to have the most efficient sources, which allows us to keep this circuit and detection as small as possible. Quickly for the software, I'm going to pass it over to Jean. As I mentioned, he is the guy who headed up all of this. He'll give you a much better explanation of the software stack that's on top than I can.
Yes, so all the magic is definitely in the hardware, but in order for you to use that, you need to have all the software stack that has been developed. And we just give you a schematic of here what is happening, because it's kind of interesting to understand why and how the job are running and what's happening behind the scene. So when the user is sending some script in Perceval from a notebook or from his computer, there is what you call a payload, which is all the requests, the description of the task that is sent to a server. Then there is multiple tasks that happen. The first one is the authentication. Do you have credits to run your job? Do you have a correct token to connect to the cloud? And then the task is put in a queue, what you call the scheduling part, where we put all the incoming job in a queue. Then there's a process of monitoring of the QPU and CPU that are behind, just that check which one is available at which moment. And then according to the priority you may have, so you may have seen on the cloud that there is a lower to higher priority on the task. And depending on the credits you have to run your task, then the task is passed to the algorithm runner, which is in charge of the orchestration of the job. And the algorithm runner will do two main things. The first thing, it will compile your task. So you are sending an optical circuit, and it will convert that into what you call a unitary matrix. Unitary matrix is transform that the QPU will apply and where we are, that is requested by your algorithm. Second part is translation. When you have a unitary, the unitary needs to be implemented inside the chip itself. And this is a quite complicated task that is done completely classically by CPU. And then when the task is transpiled, then we have a routing, sending the task either to a simulator or to one of the QPU that we have online. Then the task is going back to the end user who see the results in a few minutes. There are two main tasks that you need to understand that are happening also behind the scene. It is what you call the calibration. At every 2 hours, the QPU itself is recalibrated so that we optimize the throughput and the efficiency, the fidelity of the circuit that we can send inside the QPU. It is totally invisible for you, but it is something that is happening and self-calibrating the QPU and the hardware all day, never ending. So this is the view of what's happened behind the scene when you connect to the cloud.
Jean, I see we have a quick question related to this. Is the task type scheduler being used in the backend?
Yes, sorry. Just no, we are not using that type scheduler being used today. So we have done our own task scheduler. So we will be moving to some ActiveMQ type of scheduling that will be done behind. And there is one feature that will also change everything that we'll mention a bit later, is that the task itself will be split in smaller chunk of tasks that will be directly run on the QPUs. So there will be two levels of scheduling, one on the server side and one directly on the QPU.
Cool. Cheers, Jean. So we'll keep going. If I can click. Voila. Okay. So I also know that in the crowd, we have people with other quantum computing backgrounds, so I will tread lightly. If I make any missteps, feel free to shout at me in the chat. But we're going to compare our photonic qubits a bit to matter qubits because we can think about them slightly differently. They have different implementations. Typically, in a matter qubit, a matter-based qubit such as trapped ions, superconductors, cold atoms, your qubits are integrated onto the same chip which acts on them. We can see an example here from IBM where our qubits, highlighted here in red, are on the same chip where we have our control inputs, our outputs. So each qubit has a physical size associated with it. If you want to add more qubits, you have to increase the size of your chip. Which may increase depending on the system you have. It may increase your thermal regulation, for example, and your kind of electronic your electronic integration and all of these sorts of things. The main challenge that these kind of qubits deal with is decoherence, which is something that those of you who work in this field are probably very well aware of. When we compare this to photonic qubits, there's a lot of information here. I'll go through it a bit slowly. So photonic qubits are not static in as much as they are not built onto the photonic chip itself. The photons are generated by our single photon sources. The photons are just photons until they are put onto the chip, and at that point they become qubits. So our chip does not have the qubits integrated onto them. Rather, it only acts on them in a very classical sort of way with the beam splitters and the phase shifters that are controlled by a classical computer. The encoding that we use, I don't know if you can see my mouse. I don't know if I can see my mouse. There we go. The encoding that we use is called dual rail encoding. You can imagine this as if we have two of our waveguides, our optical fibers as such, as we discussed before. And we have a photon on the top that could represent our 0 state, and the photon on the bottom represents our 1 state. And then we can use beam splitters, for example, modulo a normalization factor here to create superposition. So if we had two modes here, we sent a photon through the top into this beam splitter. We don't necessarily know where the photon is at the output until we measure it. This is superposition. And then you could imagine cascading these sorts of beam splitter operations over a large chip, which is what you have here down at the bottom. So we have many photons which are input into the chip. They interfere, as we've seen before, across the whole chip. At the output, we get, well, depends on what calculation we're doing, but we get the output that we expect from the outside. The things to note about photonic qubits, if you don't have maybe a background in them, is that these gates are probabilistic gates. So each of these actions, the beam splitters, are probabilistic. When we want to implement CNOTs, we have to do things like herald, for example, depending on the kinds of encodings that we use. So photon generation and entanglement are both probabilistic operations that we'd implement on these chips. A nice thing about them, though, because we generate all of our photons off of the chip and we do our detection afterwards, increasing the qubit count does not necessarily increase the hardware size, especially if we start to think about using entanglement as a resource and having these kinds of feed-forward techniques. We can keep our chip in a fairly static size and increase the number of qubits simply using entanglement as the resource. Photonic qubits do not experience decoherence in any practical way that we use them. We do experience loss. We'll talk a bit more on that later, but we don't have the same decoherence concerns as you might see in matter qubits. And then a nice thing, as I touched on just before, all of this happens at room temperature. The photons generated at 4 Kelvin, the detection at 4 Kelvin, our chip, which we can change in and out, is at room temperature. So that's good. Less cooling requirements from that front. I have not offended any of our matter qubit people in the crowd. Okay, we'll move on. Very nice. If you're interested in learning a lot more about the technology, how you can use it, we have a lot of Medium articles that we at Quandela have written, single photon sources, graph problems, quantum machine learning, computations on a quantum computer, how you can actually put all of the ingredients of an optical quantum computer together, and what that actually means. So I think Lena will be sending out links for this. Again, I'm also sharing these slides so you have access to all of this material from whenever you want to look at it. But it's something that we put on quite regularly to help the community understand what we're doing and how we're doing it and why we're doing it. I'll look at the chat just to see. Oh, Alina is sharing all of that. Very nice. So now we're going to talk in a bit more depth about Estella. Estella is our implementation, is our QPU that we have online right now. And this is what it looks like in more detail. This is a bit more colorful. So we have 12 modes here. And we input 6 photons across these 12 modes. So we have the dual rail encoding. We have to divide 12 over 2. Each photon gets 2 modes. So we can put 6 photons into this device. And using this 12-mode device, we can implement any universal, what's universal, you can implement any unitary transform that you might want across these 12 modes, according to the transpilation procedure that Jean talked about earlier. Again, to highlight the magic of what we do at Quandela, it really is in the source that is quite bright, that allows us to implement this technology reliably. And then at the output, we have threshold detectors. Threshold detectors meaning if we have, suppose, 2 photons that arrive on one detector, our detector says it has clicked, it only registers 1 photon. Improving this is something that we are definitely interested in and working on so that we can have more number resolving, both within the software and the hardware. And I'm missing some things here. Ah, voila. Okay. So if you're interested, if you have a bit more of a technical background and you're interested in some of the specs of our device, this is something that you can access through the cloud. If you register as a user, you have access to these updated metrics every 2 hours. As Jean said, it updates online, so you can be up to date if you're running simulations, for example, to prepare to launch a job on the actual QPU. And quickly, what these are. Firstly, the efficiency. So that means if we send a photon in, do we expect the photon to be out with what probability, with what percentage? And we're currently at 7.4%, which may sound low to some of you, but it's worth keeping in mind that this is a world record efficiency for such a large chip. This is unmatched in the photonics world, and it's something that we're very proud of, and also something that we're still working to improve. Our measure of indistinguishability, our HAMDIP, is at 94%. And the purity of our source, the purity of the photons of the states that actually go into the chip is at 99%. Purity being, if we have a pulse that goes into our chip, is it a single photon or is it 2 photons? And we really want them to be single photons so that we can reliably do the unitary operations that we expect. If they're not single photons, then we get outputs that don't make sense. So having a very high purity is very important for us, and we're doing quite well. Gate fidelity is something we'll talk about a little bit further on, but for CNOT, for those of you who are interested in benchmarking, we're at about 90%. And finally, the coincidence rate. So this is something that's important. If you are running an algorithm which expects 6 photon coincidence rates, you might be waiting for a while for 10,000 shots because it's at 2.5 hertz. And this is directly related to this efficiency number. So this is why we want to improve our system efficiency across the chip. But if you're looking for 2-photon coincidences, for example, that can run quite fast at about 63 kilohertz. So it depends on the algorithm you're running, what you're looking for, but it's something to keep in mind if you are planning to put something on the cloud or to do any kind of simulations, or mostly just put on the cloud. So I'll show you quickly what the cloud looks like if you haven't used it yet. Let me, voila. So can everyone still see my screen? Yep, good. So if you go to cloud.quandela.com, this is what you get. This is our splash screen. I'll go ahead and log in. So you can create an account for free. This is all, it's still free and you get cloud credits if you create an account. And then this is what your dashboard looks like. So you can see I've run a few jobs already, and this is where my jobs reside as they run. So they might say waiting, they might say in queue. My jobs have completed because I ran them a few days ago. And I can see all of the information about when I created my job, when it started, how long it took. So this one took 2.5 minutes to run. The kind of outputs which I was interested in, the tokens that I used, anything you might want to help you manage your workflow is located here. You can also see the status of all of our platforms. They are all currently online, which is a good thing, 90%, as I said. And then if we want to understand a bit more about the platforms, we go into platforms on the sidebar. For instance, the QPU, we can click here. And then this is where all of the information is located. Like I spoke to you before, the clock rate, the hom percentage, the transmittance, so the loss, and our G2, which is related to our purity. And this is what the chip looks like with all of the beam splitters and the phase shifters. Oops, I'm zooming in. Voila. Here's where you manage your tokens. We have some tutorials, some videos about how you can create and use your tokens, but it's pretty straightforward. You can see the credits which you have left. So whenever you create an account, you get some free credits. You get an hour of QPU time, and I believe 9 or 10 hours of simulator time. In any case, everyone here gets some extra time if you stay all the way till the end, because we appreciate you showing up. So you have that to play with, and then when you get when your job finishes, it shows up here in the notifications, and you also receive an email. Did I miss anything, Jean? Is there anything else in particular? Is that a good tour?
No, it's perfect.
Cool. So now you've seen kind of the basic features. Let's switch back over here. Voila, voila. And this is just a slide showing you where you can find information if you would like. Okay, so we're going to talk about benchmarking for a moment because we touched on our CNOT success that we have. So here we are comparing some of our n-qubit gate fidelities to some of our competitors who have systems online that you might be able to engage with and you might be able to use. We can see that for 1-qubit gates, well, everyone does quite well. Quandela especially, we're at about 99%. Quite close to IonQ. 2-qubit gates, which in this case is benchmarked with the CNOT. Again, Quandela outperforms a lot of the competitors. I don't know if you can see my mouse. Outperforms a lot of the competitors and is on par with IonQ as well. And then finally, for 3-qubit gates, like a Toffoli gate, again, Quandela's benchmarking performance is top-notch. We have a good hardware and software team behind us who's making this very possible, and we will be publishing these results for your scrutiny, for your scientific scrutiny as we get them. Oh, okay, Jean's handling that. Thank you. Let me move on. So interestingly, this is our gate fidelity here, and then we can also compare this with the number of 2-qubit gates which you can do per second. So how quickly can we actually implement these gates? And we see that given the gate fidelities which we have and the speed with which we can implement them, Quandela does well. And I'm obviously a bit biased, but I think we do much better than than some of our competitors. For example, if we want to compare to IonQ, who outperforms us in fidelities, Well, maybe there's a trade-off that you would have depending on how fast you would want to run your algorithms, because we can implement our gates in a much quicker way using our Photonic platform. Is also something that we're quite proud of and something that we're improving. And then, as I mentioned before, because we have quite nice performance, people are using our machine and they are happy with it. So we have about 2,500 hours worth of computations across 40,000 jobs, and we are online anytime just about that you would want us to be online. Okay, we shall move on. Are we all happy so far? Cool. So here is our cloud development roadmap. So here's a graph of what we're looking to do. We have our software, our algorithms, and our platforms, what we've done in the past couple of years, as well as what we're planning to do. So I'll go through these row by row. On software, obviously, we have Percival, something that you are all probably familiar with, and maybe you've used already. We encourage you to. With Percival, you can write and run code, which can be put on the cloud. Something that we've also explored a lot here today. And then this year, we're looking to implement Mosaic OS, which is the operating system that you would have if you had one of these machines on your site, how you can interact with these devices, as well as Perceval Pro, which is something that we'll touch on a bit more later. But Perceval Pro is a version of Perceval which includes specific quantum algorithms and toolboxes that you can have access to through Pro. And then finally, we're going to continue to improve that according to the kind of community feedback which we receive, the technical things that we have to update as we go, and it'll continue to improve. That's what 2.0 is. Our algorithms and our applications. So we have entropy. We'll talk a little more about that in a couple of slides. It is a random number generator. And then we have love calculus, which is kind of a graphical way that we can interpret these circuits and optimize and implement them on our devices. As part of this quantum toolbox, these algorithms that are included with Pro, we have machine learning kinds of algorithms and entropy, and we are also looking to get more involved in finance algorithms and how we can implement and contribute to that. And then in the longer term, also implementing logistics. This means graphs, essentially graph kinds of problems, as well as chemistry kinds of problems, which can be related, of course. And then finally, our platform. So this is referring a bit more to the hardware sides of things. We have Astronar, which is our 2-qubit 4 mode, which is specialized for the random number generation. We have Estella, which is what you can access right now. So this is the 6-qubit device that we talked about across the 12 modes. And we also have a noisy simulator so that you can understand and you can predict how your applications will run on the QPU. And then coming this year, we have Altair and Belenos. So you might notice these names. Noisy simulator is not the name of a star, but the rest of these are names of stars. And maybe if this takes off, we can name a star after our noisy simulator. That would be fun. But we have Altair and Belenos, Belenos being the god of light in Celtic culture, in French kind of Celtic culture, which is a 4-qubit 10 mode specialized for quantum machine learning. We'll talk about that on the next slide. And then also a larger universal device, as well as more high performance computing, which will allow you to simulate more efficiently the devices. And finally, more longer term, 24 qubits, linear states, cluster states, these kinds of things. There's a question in the Q&A. How does love calculus compare to ZX calculus? I think Jean will have more information on this and how love was implemented. Do you want to?
Yeah, I will type the answer, but love calculus is very comparable to ZX calculus, but it's focused on linear optics. So we made some bridge with ZX calculus and we are working to make more. But the key object that you're manipulating with love calculus is linear optics, and we show that there is a complete completude of love calculus on all the type of quantum circuit that you want to design. So there is a bridge between love calculus and ZX calculus. I can send you more pointer on that, and there is a paper that we have been published describing that.
Cool. All right. There we go. So we're going to talk a bit more about the specialized circuits which I referred to right here in Altair. So why would you want to specialize circuits to begin with? As we saw in one of the earlier slides, loss is a thing that we have to compete with quite often. So if we have lower loss circuits, which can be used for specific tasks, and for example, what Altair does, optimizing ansatz circuits for QML applications, the less loss means that we can have coincidence rates which are much higher, which means we can do calculations much faster in a more efficient way than what you might expect on a typical universal chip. So it's kind of a way that we can bridge faster calculations in the more near term, something that our theory and our hardware teams are both working on. And then, for example, this is a circuit which might be available to you coming up very soon in Q2. There's another Q&A. Oh, that's the same one. Wow. And this is something that we're developing also, something that which we'll be releasing soon, and something which we'd like to continue to develop. And the idea is that there are different ways which you can interact with the hardware, with the software. You have your a bit more lower level, which would be actually coding in Percival. That means going in, preparing linear optical circuits yourself, doing all of the kind of things that might require some more technical expertise, which some of us have, but maybe not all of us. So that's it's a very low level way to engage with the machine to develop algorithms. And then on top of that, something that we're developing is what we call our toolbox. It's a bunch of algorithm primitives, for example, for solving partial differential equations, for generating random numbers in a secure and certified way, even on chip. There's security proofs, which well, the paper's been released. I think we can share that with you on the archive. And so we want to have a toolbox for users to interact with and engage with the QPU without knowing that there's a photonic circuit necessarily what it looks like behind. So we would like to have a classical programmer come along, say they want to solve their PDE, input whatever boundary or initial conditions they have, and then to send it off to the QPU without this kind of low-level programming that happens at Perceval. So this is something coming very soon. And then more longer-term developments that we're developing, that we're working on would be QBO, so binary optimization, graph problems and logistics, as we talked about before, which are very important across every field that you can imagine, as well as quantum machine learning, something that we all love and care about very much. So it's quite a hot topic. And this is where most of our user base we expect would be engaging with the software. So just to break this down a little bit further for you, we again looking at a roadmap for some of the new features that we expect to implement on the cloud. We have our cloud features, which includes notebook integration. So rather than sending your jobs to the cloud from your local machine, you can log into your cloud account, create your notebooks there, and run them directly from the online system. Oh, I've lost that. There we go. We would like to, well, we will be implementing a different billing system. So that would be based rather on the number of shots rather than the actual computation time used, which is good for you as end users, because if we happen to be running a bit slow on our QPU one day, you don't end up paying more. You pay for the actual computations that you perform, and you don't lose anything. It's a better, more fair way to be charging in the future, to be billing. Why am I losing everything each time I click? Voila. And then another thing which we're developing for the end of this year would be integrating your applications through an API into different software that you might want to be using, so that again, you can run things on the quantum computer without necessarily understanding what's going on in the background. You can implement your algorithms directly through the API and integrate that into different kinds of software packages that you might have. There again. And then Virtual Lab, updating Virtual Lab, something that will be, I believe, freely available to you. Virtual Lab is what you saw at the beginning, the simulations that we had, but we're going to be updating that, improving that, making that more user-friendly so that you can design circuits from perhaps a more experimental point of view and see what's going on the chip. And finally, running your algorithms remotely, which relates to these this kind of notebook integration. I think Jean, maybe you would like to mention this one a bit more in depth.
Yes, so this features what you got remote algorithm is actually quite important. Today, when you are running a loop on iterating on something on the QPU, then you have the full stack that I would describe before, where your task is leaving your computer and goes to the cloud and goes to the QPU. And then it takes quite some time. It takes something like 15 seconds to get to the QPU and come back. If you want to iterate on have something like 10,000 tasks in a row, it is not manageable to do that locally. So we will be increasing that feature, improving that feature, where you will be able to run directly algorithm first on the cloud, which is what you call the level 2, and then directly at the end on the QPU, where you will be able to run a task for a task, for instance, a variational task that will be executed and iterated directly on the cloud with some kind of micro task that will be sent, and you will receive the full package result. So in a few minutes, you will be able to do something like 10,000 tasks, micro task that will be run directly on the QPU.
Yeah, so the way that we can batch tasks together to streamline your calculations. And I think if I click again, I'm going to lose everything. Oh, voila. Yeah, that worked that time. Okay, so we spent a lot of time talking about the cloud. We're going to talk a bit more about Percival. Percival is the open source development software that we use to actually engage with the QPU and develop quantum circuits and quantum algorithms. So, well, as I just said, Percival is used to design and simulate and run these quantum these circuits. It enables you to experiment with the algorithms locally, as well as through the simulator and ultimately through the cloud. We have a lot of tutorials online for how to do this. And of course, if you ever have any questions, you can contact me or anyone else through the IT team on our cloud services. We'll talk about that in a minute. And it's also something which we would like to see more and more evolving with the community's needs. So part of the reason today for having this webinar is to get the word out, but also to let you feedback about things that you think are important. We have a forum through which you can do this. And we want to develop this with the kind of community spirit in mind to best serve everybody, not just us and our own technological developments. But of course, Percival will be evolving with that as needed. Things that are forthcoming will be Percival 0.8. So this is our newest version of Percival, which we have Excalibur. It's got an optimized C++ library to help with the transpilation. The transpilation is something that can be a bottleneck depending on the kind of application you're running. It currently takes a minute or so to transpile some larger circuits. We've improved that. And on the next version of Percival 0.8 that's coming out, it will be much quicker and much more efficient and much more reliable especially for large circuits, which is interesting if you're doing, for example, graph problems that might require more modes and more photons. It'll give you a much quicker and better results. Percival 0.9 coming a bit later, having more scalable noisy simulators and also photon number resolving detection. So if you have an application, maybe a QPU application, for example, that might benefit from having photon number resolution, this is a way that you can do it in our newer version, according to the simulator, and also having more efficient noisy simulators. By the end of the year, as we've discussed, we're going to support these kind of remote smart algorithms with the batching, as well as density matrix and cluster state implementations on Percival. So these are all things to look forward to. If you have an optics background, then these kinds of implementations will be very, very nice and important to you particularly. And finally, well, not finally, but along the way, I mentioned we'd like to get a bit of feedback on you. So there's a poll that probably just flashed up in front of you. It did for me. You can, well, we haven't finished the webinar yet. Maybe you have or have not found it useful up to this point, but you can give feedback on that. We're particularly interested in maybe some feedback on kinds of applications that would be most interesting for you. So we're going to pause for 1 or 2 minutes, let you have a look at the questions, and then maybe open the floor to discussion if you'd like, or highlight the important ones. So I'll mute myself now for a moment. Okay, you feel free to keep responding, but we've already got some interesting results. First and foremost, I'm very happy that you guys have found this useful so far. We've put in a lot of work. It's nice to see that. Something I've noticed at the bottom, in particular, what Percival or cloud features would be useful for you? Density matrices, that's a very good one. Connectivity with other frameworks. This is something that we are definitely aware of and want to be doing more of, so that we can integrate across as many platforms as possible for you. Something interesting that I see is having more tutorials and documentation. We have a few votes on that. If you, the polls are anonymous for us, but if you feel comfortable and you'd like to share in the chat or raise your hand and discuss what kind of tutorials or documentation specifically interests you, that's something that we can and likely will develop internally and or help you out with in some kind of way through emails. Does anyone feel comfortable sharing? You're more than welcome to. If not, it's okay. It's okay to be shy. Okay. Okay, well, we'll continue. But just to also raise awareness, we are also, myself and others in the applications and software team are developing more tutorials, are developing more documentation, and we strive to keep it as up to date as possible with each release that comes along, because we know how frustrating it can be to have your code break with each release. A little bit of that is inevitable as we develop up to version 1.0, but we are definitely trying to keep that as up to date and relevant for you as we can be, with different sorts of algorithms and ways that you can engage with the cloud. Okay. This is also the moment. We're not at the end of the session quite yet, but we will take a short break right here for anyone who would like to ask any questions that myself or Jean or someone else might have the response to. We've been asking a few along the way, but now's also the moment. We have Felix. There you go, Felix. I think you can speak now.
Yes, hello. Can you hear me well?
Yes, we can.
So thanks for the nice presentation, Jason. I have a couple of questions if that's okay.
Go for it.
My first question would be, because you showed how a user can also send the raw payloads directly through the cloud platform. Are those API specifications actually somewhere available online, or can you share them?
Sorry, Felix, you were talking about API. I missed the first part of the sentence.
Because the payload will respect the API specifications, right?
Yes.
So is there somewhere documentation or somewhere to be found like how the payload should look like?
Not yet. So today you have the payload that is quite, so it's a REST service, so you can get access to it just looking at what Perceval is doing. But we are taking a little bit of more time before publishing the specification. So in the roadmap, I think it was in Q2 that we will publish API for other language, and then that means that will be able to integrate with any type of other application. But we don't want to publish it yet because we are afraid that we'll be breaking it if we do it too soon. So give us 2-3 more months and it will be there.
Okay, great, thank you. And with that, you already answered my second question, which would be also like, because you were talking about the cloud. This is basically means you have a web service hosted somewhere in the cloud that actually like handles all the user management and scheduling authentication that you mentioned in the beginning, right? So you have like, from the architecture perspective, what you have is actually the SDK that someone locally downloads, like Percival, and then what's actually in the cloud is that web service that exposes your Acela.
Exactly. So it's what Perceval is able to do today, you will be able to do that from any type of other type of clients tomorrow. So it's not just public, but everything will be exposed, and you will have this is integrity, authentication, credit management, and everything.
Okay, thanks. And then because you also mentioned compilation in the beginning, my question would be, because when I look a bit at the Percival Python API, it's formulated in terms of beam splitters and phase shifters. So basically in components that I would see also on the chip. So when you speak of compilation, is there do you mean something more than mapping?
Yes, it's a bit more than that, because so today we have made connector with Qiskit, for instance, and we are working with connectors with other third-party tools. And then for this type of circuits, it's more than that. It's transforming any type of third-party logic to all logic. So of course, if we start with a beam splitter, then at the end the compilation is very simple. You get at the end, you are quite sure to be on the beam splitter. But we have also some operators that are not available on the chip, for instance, time delays, and this requires some compilation. So the straightforward answer is, if you have very simple basic circuit, then you are quite sure that it will be implemented as such on the chip. If you have more complicated or circuit that doesn't use linear optics, then we need the compilation phase.
Okay, so that means if I send my circuit from Percival, where I can formulate my circuit in terms of hardware components, there is like a low level of compilation in terms of mapping. But if I would send a circuit in the future, let's say with Qiskit or some gate-based framework, there would be like a level of compilation that you build in that stack.
Yes, exactly.
Okay, okay. And my last question, then thanks for like letting me ask so many questions.
No, go for it.
My last question would be, because you mentioned also that chip has a world record efficiency, so to speak, like ultra low loss. Is that your chip? Like, do you fabricate your chips yourself, or do you get them from a third-party vendor?
So the efficiency that you are mentioning is the end-to-end efficiency. So it takes into account the brightness of the source and all the transmission, the DMX, the detector loss, everything. So it's not just the chip efficiency itself. It's you need to add up with all the loss that you can have along the way. The chip that we have two chips on the Estella and Acana. They are coming for two different providers today. One is on glass, one is silicium based. They are not. We have not produced them.
Okay, so are these commercial products? Can you say that, or do you get them like other commercial products? Okay, great. Thank you.
They are commercial product.
Thank you.
No, thank you, Felix. Do we have any other questions? We don't have super long left, but I don't have but one or two more slides, so we do have time for questions if people have questions. Okay, I think we'll continue on. So the last bit is just, if you do start to engage, we hope you do, how you can be in touch with us to ask more questions, for support, technical. I'm also here for emotional support if you ever need. You can send me your thoughts. So if you have any questions about Percival, first you can go to the GitHub to see what's happening, and also ask us questions on the forum. This is our community-based forum for any kind of technical Percival related questions, like some of the ones we just had from Felix. Cloud related questions, if you are interacting with the cloud and something doesn't make sense, doesn't behave like you expect it to behave, if you have any ideas on what you would like to see, things that can make your life easier, we are open to all, and we are quite responsive. If you have read Brian Siegelwax's Medium article, then you will know we handle our tickets as quickly as we can. And that's on the cloud support page as well. It's a little support button, as you can see from the cloud.quandela.com that I showed you earlier. Stay tuned for other events. We'd like to host these kinds of webinars regularly to keep you guys up to date, to give you a chance to ask questions, to give us feedback, positive, negative, anything that you would like. That's what we're here for. So there are events both happening online as well as some in-person events that we hope to be sharing with you in the future. So follow us on LinkedIn or any kind of professional resource like that. And feel free to engage with any kind of community platform like we have through the cloud. Thank you very much for joining us, and please do stay tuned for more events coming your way. Thank you all very much.
Thank you very much. And feel free to send questions after the event if you want. We'll be there.
We're always here.
Thank you all.